All right, so the topic tonight, let me get this going. Kayla, can you confirm that everybody can see my screen, everybody can hear me?
Yep, everything looks good.
All right, great. So our topic tonight is the geology of the Susquehanna River. As Kayla mentioned, I work for the Susquehanna River Basin Commission, and we are a federal interstate compact. That sounds like a mouthful, I understand. This came out of the 1970s. We had a lot of environmental concerns throughout the country. Some of you may know Silent Spring by the book by Rachel Carson. There's also Love Canal and so forth. And out of that, the states and the federal government looked at a basin-wide approach to managing water so that the citizens in these basins have accessible water, clean drinking water, also water used for industry and whatnot. So we were founded in 1971. It was a pretty big endeavor. Mostly because we had to go through Congress and trying to get 3 states and the federal government to agree on something, as you can imagine, was quite daunting back then. I could imagine doing it now. But we've been around since 71 and we have a 50-year compact, which can be renewed. So we still have some time left. Quick facts about our basin. Here on the right is the typical map that we show folks. The Susquehanna River Basin is comprised of 6 subbasins. Starting from the upper part on the northeast side, we have the upper Susquehanna. Then we have the Chemung, the middle Susquehanna, which you may know as coal country, Scranton, Wilkes-Barre. We have the west branch, which is also coal country. We have different types of coal on that side. The Juniata with, of course, Racetown Lake, the 2nd largest reservoir in the basin. And lower Susquehanna, where we currently are. Pretty big basin. It's not the smallest, it's not the largest. About 27,000 square miles. We're about half of Pennsylvania, much smaller portion of obviously Maryland and New York. Although we are 43% of the Chesapeake Bay watershed, interesting fact, we provide over 50% of the fresh water that goes into the Chesapeake Bay. And more importantly, the upper bay, if you look down at that map, the Havre de Grace down in Hartford County, almost 85% of all the water in that upper portion of the Chesapeake Bay comes from the Susquehanna. So it's a very important tributary. A lot of people down in the bay rely on that clean water we send down, hopefully, for their livelihood and for recreation. And on average, we're putting about 18 million gallons a day per minute. If you can envision that, it's pretty quick into the bay. So now that we got the SRBC out of the way, let's talk about geology. Before we hop into the geology of the basin itself. What is geology? At the basic level, from the Latin geo, which means earth, and ology, the study of. So it's a study of the earth. That's pretty broad, and it is. It's one of the older disciplines. It comes from the philosophy branch of the sciences. And generally speaking, we are scientists that deal with the history of the earth, and our books are rocks. We look at rocks and try to decrypt and understand. But it's not just rocks. We also look at all materials. It could be sand, water, air, and there's even such things as space geology, which is kind of neat. If you guys know about the Mars rover, and I'll talk about that here in a second. And generally speaking, geology is a study of all materials above and below the surface and its history and how they relate to each other. So it's pretty broad. And so what's interesting is that you get different kinds of specializations. So I don't know if you're familiar, there's physical, volcanologist, mineralogist, hydrologist, hydrogeologist, space geologist, which I prefer over astrogeologist. I think it sounds a little neater, and marine geologist. And there's many more specialties. You can really get down to some pretty detailed type of geology. So what are these disciplines? And they all kind of relate back to the geology of the basin, because we have the first one is a physical geologist. Physical geologists look at the structure and how they interact. For example, here you see some folded bedrock and cracks. They look at these, they try to figure out how old they are, relate them to it, how water interacts with them, if there's any minerals that are useful for mining and or industry, and also is the rock good enough to build on and so forth. The next geologist, which this is the one that in college everybody gets really excited about, because these are kind of an adventure, in the field, very dangerous. It's probably the only type of geology or geologists that actually work with live geology. Volcanoes is the active process of making, new rocks and so forth. So, not my bag. personally my cup of tea. It's a little more dangerous. There have been many volcanologists who have perished, unfortunately, but their science has been very useful in figuring out a lot of things. So we do respect their work, and it's quite a feat. The next one is mineralogist. This might be kind of self-explanatory. This is where, you know, we get all our diamonds and our other beautiful minerals and rocks. You can see this fellow here is very excited about that very large piece of quartzite he has there. This is, I guess, would be the most forward-looking. Most people have interaction with geology. They see gems and rocks and agate and so forth. But mineralogists actually delve down into the chemical structure, how they interact, figure out, you know, can this mineral be used for face powder, or can this be used for an insulator or a battery like lithium? Very, very important for the progression of modern energy and other industries. The next one is hydrogeologist. That's what I am, my specialty. Hydro, water, geologist, study of the earth. And unfortunately, I don't have a very good picture because what we do is not very visible on the surface. We drill a lot of wells. What you see here is, I forget where I was drilling this well, but essentially we drill a well, we see the water, we test it, we pump it. A hydrogeologist really focuses on the fresh water and how it relates to rocks. So for example, if you're in a public water system, a hydrogeologist would go out and site a well, try to find a good source of clean drinking water that can be used for the system. That's kind of what we do. We also deal with stormwater, some other issues as well, but that's our primary function. The next geologist is space geologist, which I think is fascinating. It's one of my favorite things to read on. And I mentioned before the Curiosity rover. NASA's done a lot of things that have really helped advance. Before, astrogeologists or space geologists only really had to rely on large telescopes and light. And so a lot of it was very theoretical and hard to get boots on the ground. Most geologists like to pick up the rocks and feel them. In fact, that's one of the things that's unfortunately being through Zoom is I have a whole box of rocks I would have brought to hand out for people to look that come from the basin, but maybe another time. So space geologist is really fascinating, and the Mars rover has been very instrumental because it's actually it's a geologist. It's a drill. It takes specimens. It measures the chemical. It's doing geology on a whole different planet, which I think is just absolutely fascinating. And I look forward to the new telescope that was launched here. I think the James Webb Telescope, and hopefully that'll provide some more information for our space geologists to find new interesting things about our universe. And the last one, which is sometimes underlooked, you've heard probably of marine biology, right? That's a lot of people want to be marine biologists and have fun with the dolphins, but the marine geologist is equally as important. A lot of people don't realize that a lot of our materials and a lot of our industry, oil and so forth, come from the ocean. And if you really think about it, you know, the earth is what, 2/3 covered with oceans. There's more geology under the ocean than there is above the ocean. So they have a much larger playground to play in, and it's a lot more difficult. You know, I can go out to, say, the PA Grand Canyon and measure some rocks and take some samples. Meanwhile, a marine geologist, it's a little hard to get down 10,000 feet under the sea in a submarine and try to pick up a rock where it's dark and cold and there's no oxygen. So they're kind of the unsung heroes, and they're doing a lot more work with geophysics so they can measure things from the surface, but it's kind of a neat discipline as well. And as I mentioned before, there are many, many more geologist types. If anyone has a fancy, I'm sure you can find a specialty on it. So don't be afraid to go out there and look up. I'm done with my pitch for geologists since we're kind of a dying breed. So hoping to recruit some people and spark some interest. So the geology of the Susquehanna River Basin. Let's start with just the basic rock cycle. Many of you have heard about the water cycle. There's a very similar cycle that is in rocks. So what you have before you is essentially we have an uplift of geologic materials above the water level. And as that is uplifted, you have weather and snow and ice and even gravity that kind of weathers those hard rock surfaces and transports them down to a sedimentation area. I think if you go to the beach, you see all that sand originally started from way up in the mountains, and it slowly made its way down to the beach and created our nice beaches and our sandbars. Well, once that sand has been placed out in the ocean for a while and you get layers and layers of sand, it starts getting compacted. And not only is it compact, but at a certain point, the pressure and the temperature causes the sediment to actually form into loose rock. Sedimentary rock is what we call it, and then harder rock. And that's where you have your basic rock types: sedimentary, metamorphic and igneous. Sedimentary is deposited from materials that are from the surface of the earth and then compressed. Metamorphic, as it goes deeper and it's pulled down underneath, right? As the continents are going up, the sedimentary rock is pulled through. More pressure and heat is applied to it. Almost like if you've ever seen glass blowing, glass is a sedimentary rock, it's sandstone essentially. Well, once you heat it up and start pressing it and turning it into a vase, you're metamorphosing it and adding color and adding different minerals. It's a very similar process. Now, if that metamorphic rock comes up to the surface, then we get to look at it. And I'll show you some of these maps that we have here in Basin. But if that metamorphic rock is actually pulled down into the molten core or the lithosphere of our Earth, it actually melts down, much like you would melt, ice into water. At which point it's this bubbling cauldron of very, very hot magma, which once the pressures and the water in it kind of boil up, just like you would be boiling milk, it wants to come out to the surface. And that's how we get our volcanoes. Once the volcanoes are up to the top, then the whole process starts again. And it weathers and erodes, and that material is transported down through our streams and down to the ocean, and the whole cycle starts again. That's just a real basic overview of the rock cycle. Now, I mentioned before there are three basic types of rocks, categories. Sedimentary, so self-explanatory, it's sediment that has been laid down. So you've all known about sandstone, shale, of course, limestone. Living here in central Pennsylvania, we have a large limestone contingent. Conglomerate, which is where, if you could imagine a bunch of gravels that are compressed into a rock layer. Some of you who travel up north towards Scranton may know some of the rock formations up there called the Pottsville. It looks like concrete, but it's actually a natural rock formation. And then gypsum, that falls under an evaporite. We don't really have much of the gypsum here in the basin. In fact, not that I know of there are any large formations. But essentially, if you can imagine the Great Salt Lake out west, the water comes in with lots of salts, evaporates, and then a deposit of salts or gypsums or whatnot is laid down, and then that's buried and turned into rock. So those are the type of sedimentary rocks. Once those rocks have been created and they're pulled down or pushed or deformed, they become metamorphic. They morph into something different. So here you can see you have marble. Well, if you take limestone and apply heat and pressure, you get marble. If you take shale and you heat and compress it, you get slate. If you take sandstone and you heat and compress it, you get quartzite. If you get gypsum and conglomerate and other materials and you compress it to the point where the materials are all jumbled together, in other words, you take your limestone, your sandstone, your shales, and compress it into one rock, you get what's called gneiss. And there are a lot of really bad geology jokes I could make about how nice this is, but I'll just stop there. The last one is the most interesting. We'll call these the deep rocks. These are the volcanic, the magmatic, the deep, heavy rocks. I'm sure some of you may have some granite counters. It's a much denser crystalline-based rock that's from deep down in the ground. In other words, we take our sedimentary and our metamorphic rocks and we melt them down, and then when they solidify or refreeze, if you will, they solidify into these bigger crystals, and they don't really have the same properties as sedimentary or metamorphic rocks. And what's really interesting is down below the ground, when we take in limestone and put it into a heat, there's a lot of gases in limestone, and when it's under pressure, it creates these bubbles. And if you've been to a Bed and Body Works or some sort of beauty store, you've seen pumice, which is very light rock. It's full of holes. Well, that's from the gases when it's outgassing coming to the surface. So those are the three basic rocks. The last one here, obsidian, we don't have in the basin. It's essentially volcanic glass, which is related to quartzite, which is also glass, which is related to sandstone, which is typically also silica and glass. So there's a lot of interrelationship. It's just different forms and pressures and different ways of baking the cake, if you will. Now, the next thing we have to talk about before we start talking about our basin is plate tectonics. How does this work? So back in the 1900s, there was a thing called continental drift. In other words, geologists at the time thought that the plates were just the outline of the continents. For example, here in South America, if you can see my cursor, they thought that's where the end of the continent was. Well, fast forward about the 1930s, and a couple people said, well, actually, we're finding evidence that the plates are actually really, really much larger, and some of them are completely underwater, and they don't even have land expression. For example, here, the Juan de Fuca plate, which is responsible for the Mount St. Helens volcanoes and those Cascade volcanoes up there, there's no landmass above the water, but it's still an individual plate. So these plates, move around our planet over time. And how they do this is that our Earth is almost like a golf ball, with the center being a very hot molten core. And that molten core acts like an engine. In other words, plumes of magma come up and it pushes against the plates, which pushes in a direction. And then the plates, when they hit each other, they interact. You take two cars and you smash them together, they kind of move to the side and so forth. So that's the basis for plate tectonics. So once we understand there's the type of rocks we have, we understand how our plates move around the world, we can start looking at how our Susquehanna River Basin was formed. So we're going to go through a little history. It's interesting that you mentioned the previous lecture was on the history of Wildwood and Susquehanna River. Here, geology is about the history of rocks. So we're going to start our story here about 740 million years ago with a supercontinent called Rodinia. Mind you, a lot of this is done through drilling cores and some guesswork. So, the dates are not 100%, but they're, relatively off their relationship wise. And what we have here is we have this supercontinent completely surrounded by other supercontinents smashed into it. Now we fast forward about, to 582 million years ago, and now we have Laurentia. Laurentia is essentially what will become North America, plus or minus some additions graciously given to us by Africa and Europe and also some of the other plates. What's interesting is if you've ever been up north in the basin, we have the Laurel Highlands. Laurentia was actually named after Laurel, which was the old area up there in north. So there's a connection to our basin. About 512 million years ago, Laurentia finally got free of all the other continents that just kept hogging its coastline, and we became a very large continent with lots of ocean and coastline. And this is important because today, if you look at the coastline, say down at Wildwood, New Jersey, so all that sand and so forth is materials that are there. And so this continent was producing a lot of sedimentary debris on the sides. And this will come into play here in a second, and I'll explain why. So now that we have a free Laurentian continent, free finally at last, unfortunately, the African plate had a different idea. I decided to come and give us a little love tap. Here, it's on the east coast of the North American plate. Specifically here, if you look in the corner, there's a little jutting out, and this will come back into play, and I'll show you in some maps. And then over here is the Eurasian plate that's also at the same time decided to gang up and also kind of push us and squeeze us. And then finally, around 150 million years ago, the African plate decided, hey, you know what, I'm good, I'll see you later. And you can start to see the North American continent kind of form a little bit, right? You see Alaska here in the north corner. Here's what will become Baja, Mexico. And then here's the eastern seaboard, and then northeast where the Eurasian plate is. Like I mentioned before, one of the ways that rock is generated is through plate tectonics. And although there's a difference between the plate tectonics that occurred for the Appalachian Mountains and the plate tectonics that occurred on the West Coast. On the West Coast, we had an ocean plate, the Pacific plate, which is denser. And so instead of smacking up against the North American plate and creating tall mountains like the Appalachians, it actually subducted below it and created magma in the mantle, in the lithosphere, and created all the volcanoes and the chains. But because there was a plate on the west and a plate on the east, we get this general consensus. 54 million years ago, we have the Appalachian Mountains on our east coast. We have the Rockies in the center that has been compressed from the west and the east. And then with the Sierra Nevada mountains that are a little bit closer to where that plate was. And of course, the volcanoes that occur out west. And then finally, around 44 million years ago, Europe decided to go back to where it wants to go. And we generally have our continent the way, generally the way it looked, with some minor variations, of course, but we've been relatively stable for the past 44 million years. And that's kind of the quick history of how we got to the North American plate, of which the Susquehanna River Basin is part of. This map is one of my favorite maps. It was created in 1902. It's the physiographic diagram of the United States. And it really shows well what we were trying to illustrate here before about the history of how the geology was formed. You can see here the Rocky Mountains in the center. You see the Cascades. You see the Great Valley that's over in California. And then here on the East Coast, you can see our Appalachian Mountains. And remember when I pointed out that Europe and Africa came together and made that little point? Well, you can still see that point today here. In fact, that point is what we would call Cumberland County, the hinge of where Africa and Europe decided to butt up against us. Here's a more recent version created by the USGS. This is from 1990 using satellite imagery, yes. And again, you can see here in the corner that that's Cumberland County. That's the hinge where Africa kind of hit up to it. And you can see how it was kind of smushed and squished by the other two plates. And that'll come very important to the Susquehanna River Basin down the road, because it really is what sparked our geology, what made it so unique for our basin. And that's something a lot of people don't realize. Both Pennsylvania and the Susquehanna River Basin, our geology is rather unique in the world. It's interesting that our rocks go from 10,000 years ago from the glacial age all the way to about 540 million years old in a matter of about 100 miles. So if you travel from, say, Lancaster up towards, say, Tioga County, you're traveling almost 500 million years of geologic history. It's pretty interesting. And so, as geologists like to do, we like to sort things and put things together. Here's a closer look of the physiographic provinces, which is from the physiographic map. We try to keep things together. You see the Valley and Ridge province, the Appalachian Plateau, the Blue Ridge Mountains, which we call South Mountain. There's only a little portion here in our basin and in the state of Pennsylvania. And of course, the Piedmont, which is the plain that's further down. But we'll get into that here in a little bit more detail. So here's our basin. The Susquehanna River Basin here, I should have mapped before, but here's with the physiographic provinces. There are two on here, the Catskill Mountains, the Northeast, and the South Mountain section, which is not a province. It's an outlier that has been kind of a stepchild for a while, where it's not really part of one or the other, and it's just an oddball, and it's kind of interesting. And then the Catskill Mountains up in the Northeast there's so little of it that there's no real change with the Appalachian Plateau province. And so we kind of lump it in together. So generally, we're going to go over the three main sections: the Piedmont province, which is where we live here; the Ridge and Valley province, which is the State College area, if you've driven up there; and the Appalachian Plateaus, which is like the wilds where all the elk are, and the PA Grand Canyon and so forth. Now, interestingly enough, this is what our basin looks like if we just look at the topography or the elevation difference, understanding that the highest points of our basin are actually to the northwest here, up towards Tioga and McKean and Potter County. And the lowest obviously would be down here at the basin exit, which is Havre de Grace, down at the Chesapeake Bay. So generally speaking, elevations increase as you go northwest, although up towards the Catskill, you do get the Catskill section, you do get some larger mountains there as well. And here you can see some of the river, part of our basin rivers here, how they interact. Now, a lot of people ask, what does our basin look like? And at work, when I first started working for the commission, the first thing they told me, oh, we have a turtle hobo. I was like, what, a hobo turtle? Well, if you put an eye on it and you give them a knapsack, then yeah, I guess our basin kind of looks like a turtle going up for a walk. So that was kind of interesting, because it's hard to figure out, what this looks like aside from anything else. But what's also interesting is the fact that our rivers run in very, very, very different directions. I mentioned before, we have 6 subbasins, and each one has a major part of the Susquehanna River. For example, here I'm showing the Juniata and the West Branch. They go in a northeast fashion, right? Almost north, and some parts of the Susquehanna go due north. And then we have the Chemung, which goes southeast. Then we have the main stem of the Susquehanna, or the North Branch, that goes almost due west. And then finally, as it meanders down, our river goes southeast. This is all being controlled to some degree with some of the geology. And so our river is helped carving out, our canyons and creating. It's a very powerful force. However, the rocks also have some say on where the water goes. Even though rivers like to go the path of least resistance, the geology has a different mind sometimes. And here's just like a general basin map of our geology. This is very, very generalized. There are a lot more formations. I think we have over 500 in Pennsylvania alone, but that would make the map a little too busy. But again, you can see the provinces. You see the Appalachian Plateau, kind of very uniform. And then you have the Ridge and Valley province. And then down here, you have the Piedmont. And then right here is the little South Mountain, the little outlier that's kind of interesting. So let's focus in on the Piedmont. This is where we live. Cumberland is right here. We have Dolphin. We're right on the border between the Ridge and Valley and the Piedmont. This is what it looks like close up. Here's South Mountain to our west here. And you can see the streams are pretty general here. But once you start looking into the geology, we start getting into some very interesting characteristics. In fact, the Piedmont province is, I think, very, very interesting from a geology standpoint for a lot of reasons. For one, it has a part of the African plate that's stuck to us. That would be all these granites and whatnot, and quartzites and so forth that are down here towards the southern part of the basin. So when African plate came and hit us, they actually left part of Africa behind. And conversely, if you go to Africa where it hit us, you can find some of our rocks over there as well. So it's a mutual cultural exchange, if you will. But see, you can see here, the red is probably the most significant thing I want to point out here. And here it's listed as the igneous felsic or igneous mafic rocks. You know them probably better as diabase. And I'm sure people who travel around this area have seen diabase, the road cuts and whatnot. In fact, if you go to Gettysburg National Park, Devil's Den, those are all very large diabase boulders. And diabase is intrusion. So in other words, we had rocks here, and then when the plates collided, the magma wanted to come to the surface, but instead it went through the cracks of the existing rocks. In fact, Little Round Top is also diabase ridge. That's why it's a ridge. Diabase is a much harder rock, much denser. It's closer to granite than it is to anything else, but it does provide some very interesting characteristics for our water in the basin, mostly in the term of diabase dikes, which is what you see here. Now, a diabase dike is very similar to the diabase boulders I showed earlier here, except that they're very thin, but they extend several hundred to 1,000 feet down below the ground, and they are almost impenetrable. In other words, water can't get through it, other materials can't get through it, and they act like underground dams. This is kind of important for areas down in Gettysburg because these diabase dikes actually keep some of the groundwater around, even though the rocks there don't hold as much. This is also the formation where if you're a gold hunter, if you like to pan for gold, diabase is probably the one and only source of gold you can find around in the basin. So down towards Dillsburg and Wellsville, known as the Golden Triangle back in the 1800s, if you pan some streams, you can usually find some flake gold here and there if you find the right sand type, and that all comes from this deep magmatic earth known as diabase dikes. And diabase dikes also help with our river. They kind of impact the way our river is. So I want to show you here, this is a quarry up by Bainbridge called the Billmeyer Quarry, and I'll talk about it later here in a second, further down in the talk. And right here is a diabase dike that cuts across the river. That's the Susquehanna. In the background here, you see the waste to energy facility of the Lancaster County Solid Waste Management Authority. And these are the White Cliffs of Conoy. I've been there. It's rather idyllic considering it's just a pile of old limestone from the old quarry, but it's a very nice place to actually see the river and look across. But the diabase here cuts through and impacts the river. The river's going across it, even though the diabase is holding up, to show you how it interacts with groundwater. And then lastly, some of you may know about the potholes that exist down by Falmouth, which is not far from where the Bainbridge quarry I just showed you is. This is what diabase and the river, when they spend millions of years together, these are called potholes. And what happens, and the next picture is probably a little clearer, is as the water flows over the hard diabase, little pebbles, quartz pebbles that are technically slightly harder than the diabase get lodged inside, and they start to swirl and funnel and slowly dig down and create all these potholes. This is a great hike down by Falmouth, especially when the river's low in the summertime. And there's other areas closer to Safe Harbor, the downstream part of Safe Harbor Dam, where you can see these and kayak around it. They're really impressive. And these areas are also where we find a lot of our petroglyphs from our Native American friends who used to live here. So it's really fascinating to go hike and check it out. And I like to go there once a year just to clear my head because it's very, very pretty. It's miles and miles of this. All right, so next up, we're going to go to the metamorphic rocks. We do have a lot more here. And in fact, that's probably where most of our metamorphic rocks exist in the Piedmont province. And we're going to start with slate. Remember what I mentioned earlier, that slate is when you take shale and you compress it. And this is the Peach Bottom slate. It actually extends past our basin, through our basin, down into Maryland. I think even almost to West Virginia, if I'm not wrong. But it's really interesting because if you drive around Harrisburg or even Hershey, Marietta, I believe even Camp Hill, some of the houses, they have this slate on their roof. And it's actually very, very well-known slate. This historic marker, although it's from Maryland, I found it better than the Pennsylvania one. The Pennsylvania one actually talks more about the history, but the fact that in 1850, they took our Peach Bottom slate from our basin and then hauled it all the way to London. and it won first place for best slate in the world, which I thought was rather interesting. So it's unique that a lot of the history and the industry that occurred in Pennsylvania is thanks to its diverse geology. If we hadn't had slate that would occurred when the North American plate turned our shale into slate, well, that's one less industry, and it's kind of interesting. And our houses wouldn't be, and roofs wouldn't be in the full this beautiful slate. And then South Mountain. So like I mentioned before, South Mountain is kind of a unique outlier. It doesn't really fit in. It's called the Blue Ridge down south. Catoctin Mountain, if you ever go down towards Maryland, Camp David area, that's the same mountain range. And it's essentially sandstone that has been metamorphosed into really hard quartzite, in fact, harder than normal quartzite. And one of the best examples, and one of my favorite places to go during the summertime, is Pole Steeple by Laurel Lake. That's a state park there. And it's a ridge builder, and because the rock is so resistant, right? It's a quartzite, which is almost like glass, what you would have on your phone or even in your hand. It's inert. In other words, there's no atmospheric deposition, or water doesn't really do much to it. It needs physically broken down into sand granules, as opposed to say other rocks like limestone that can actually be dissolved, which I'll talk about here in a little bit. But that South Mountain is a very unique geologic feature, and kind of is the hinge where Africa and Europe hit the North American plate and create our basin. And it's also the hinge where Cumberland County and Cumberland Valley kind of shifts from north-south to east-west. A lot of my friends who come from down south, they say, well, I thought I-81 was north to south, and then they're traveling through Cumberland County and they go, this is east to west. And I say, well, the geology made it so it had to go east to west for a little before it turns back up. So, but this is a great place to go hiking as well. We also have a lot of limestone down in the Piedmont area, but the limestone that we have in the Piedmont, because it's part of this metamorphic and igneous and kind of compressed area, is a little different than what we would find, say, in the Cumberland Valley or even up in Center County. I'm going to bring back this quarry again. Here's another picture of the quarry. You can see the white cliffs of Conoy there on your right, right here. And then over here is that diabase dike I mentioned before, crossing the river, and actually crosses all the way here, and that's what makes this ridge back here. But that diabase actually impacted the quarry. And here's a face, and I took this picture while I was doing work out there. And if you want to find out more, we have a project that we do out there at Bainbridge Quarry. And when the diabase came through, on top of the fact that the African plate smushed it, our limestone here has been kind of really turned upside down. This is a really interesting picture. If you can see my cursor, you can see here that some of the limestone and dolomite has been pushed over other parts. You can see right here, there's a small fault straight up and down being shifted. There's another one right here. And a lot of that is because the diabase went through and pushed it. A lot of it was the North American plate. So all this geology is kind of interact to create a unique environment. And this, because of what happened here at the quarry, this dolomite was actually pure enough to mine for lime. Most dolomites have too much sand in it, and they stick to limestone. So you can see how the geology creates new opportunities as well. All right, we're going to transition to the Ridge and Valley province. It's a pretty self-explanatory province. I heard a lot of people call it God's country when you travel out towards Bedford, because you have these small narrow valleys with the sunsets that are parallel with the setting sun, and they are absolutely stunning, beautiful places. Excuse me. And the Ridge and Valley, that most people associate kind of with Center County. If you go to Penn State or coal country, it's very up and down, small narrow valleys. You have Dolphin, up here north of Harrisburg. You've got Stony Creek, right? Very small valley. And again, I'm going to bring this map up to show you that we have the Piedmonts down here. We have that South Mountains right there, that hinge. There's Cumberland County. And then what we have is the Ridge and Valley. And the Ridge and Valley does extend quite a bit up north and down south through Virginia, all the way down North Carolina, and the Great Smokies. The backside of the Great Smokies into Tennessee, this is the Great Tennessee Valley right here behind it. That's all the same formation. And it was all caused by the African and European plates coming up and tapping us pretty hard. Here's a really good aerial photo of the Ridge and Valley. You can see that there is, in fact, as it's described, ridges and valleys, and it's really interesting that the river normally would probably like to flow the other way, but instead it finds gaps, water gaps, wind gaps to get through it. And that's another interesting part of the geology here, is that The ridge and valley was not quite as ridge and valleyed, say 100 million years ago. And so the river was on top of it. And then once it got stuck in these water gaps, which we're familiar with the Harrisburg water gap right here, Wildwood's right about here. And then you can see here, this is Raystown Lake over here, to get an idea. And then this is Williamsport, makes that turn, and that's the end of the ridge and valley. Closer to where we live here is what it looks like up close. And you can see how the river is impacted by these ridge and valleys. The river here comes through, there's the Juniata coming in. You have the main stem, and then it hits this ridge, this strong ridge, Harper's Ferry, I believe we call it, or no, the Clark's Ferry, sorry, we're wrong part of the country. It hits this ridge and it finally finds an opening, and then it starts going south because it's trying to get to the ocean, right? That's what the Susquehanna wants to do. And it finally makes it through this valley, and all of a sudden it's up against another ridge, and so, well, let's go this way. And it finds another gap. This would be the Dolphin Narrows. Everyone's familiar with it, Statue of Liberty's there. And then it comes through and it gets to Harrisburg, which Wildwood is right here. And that is the boundary pretty much between the Ridge and Valley province and the Piedmont province. We live right on the difference. So very interesting and very productive. And there's a lot of materials and stuff that we get from the Ridge and Valley province, which I will go into here in a second. The first one I want to talk to, let me back up real quick, is we have the limestones between the Ridge and Valley and the Piedmont. And this is probably what you guys are very familiar with, is, of course, sinkholes and surface depressions. It is a way of life in the basin and the Commonwealth of Pennsylvania, but it does provide some very good resources because those large sinkholes take a lot of the stormwater and put it into the groundwater for later use. One of the reasons we're a very water-rich state is because we have some of the best limestone aquifers in the world. In fact, to my knowledge, I believe the largest well in the Commonwealth of Pennsylvania is down towards Boiling Springs, where they are tapped into a nice limestone aquifer. I tested it when I was in consulting, and we brought in the biggest pump we could fit in the hole, and at 2,000 gallons a minute, it wouldn't go down. It didn't even put a dent in it. So we're very lucky in the basin to have these large underground groundwater reservoirs that are typically in limestone. There's some other reservoirs as well, but they're pretty important. And the reason why they're important is that limestone, I mentioned before with whole steeple that quartzite and sandstone is chemically resistant. In other words, if you put acid on it, nothing happens, but if you take a hammer to it, you can break it down into smaller pieces. Limestone is the opposite. Limestone is actually technically harder. Think concrete, right? That's why we use concrete, limestone, calcium. That's why we build a lot of our buildings, very strong material. However, it is very, very susceptible to chemical weathering. In other words, back in the 70s and 80s when we had acid rain, it accelerated a lot of the cave formations and a lot of sinkholes in the area because the acid likes to eat the calcium. Calcium is a positive ion and the acid is a negative ion. And so they form together and say, hey, I'll go for a ride. It does create for some spectacular caves and springs and even sinkholes, although if it's on your property, I'm sure you're not very excited about it. But this is both a blessing and a curse. Yes, we have to live with sinkholes, but the blessing is the fact that we have plenty of good, clean spring water. A lot of people talk about that good spring water. They're usually talking about limestone. There are not a lot of very large limestone reservoirs in the nation, and we happen to have two of the largest ones. So that's a real good benefit here. Next up in the Ridge and Valley, the other most prominent known commodity is, oh, I forgot about the cave. Sorry about that. The limestone also in the Ridge and Valley creates beautiful caves. This is Penn's Caves, one of my favorite caves because it's at an angle. Beautiful, same thing you can see here where the limestone has actually been completely weathered out chemically from the rocks, from the rain and underground streams. And then you have the stalactites and stalagmites as the groundwater above it filters through, it brings more of its calcium, it's trying to refill itself, right? We have a lot of caves in Pennsylvania, wind and limestone and Penn's Cave. I think there's Indian Echo Caverns here near Hershey and Middletown. I think they're amazing. Some people are claustrophobic, but this is a pretty accessible one. It's a pretty simple ride. The next part I want to talk about is probably the most important part of the Ridge and Valley economically is, of course, our coal regions, specifically the anthracite. I'm only going to speak about the anthracite. We do have bituminous coal here on the western part of the Ridge and Valley out towards Altoona, and then, of course, in the Appalachian Plateau out towards Clearfield in Indiana. But the anthracite, I think, is a little more interesting because it's a very unique coal. It doesn't exist all over the world. In fact, I believe some of the coal measures we have found the quality of it have found nowhere else in the world. To this day, anthracite coal is actually being mined and shipped out to all over the world because it's used for making industrial steel for medical devices, and it's so pure in carbon that they have to use this stuff. So it's a kind of interesting. Again, you can see the ridge and valley. Here you are in Harrisburg down here in the corner. Wildwood's like probably about right here. So you can see the coal fields actually all the way to Dolphin. In fact, Stony Creek, if you've ever taken the trail there, that is actually an old coal railroad that used to follow up through here and provide a lot of the coal that Harrisburg and the West Shore and Hershey used to heat themselves and whatnot. So it's kind of interesting. And you have the major fields. This is the Lackawanna Canoe, as we like to call it. It's a giant canoe-like formation full of coal, and you have Wilkes-Barre, Scranton, the typical. Then you have the Hazleton coal, which is slightly different as well. Then you have what I like to call the Schuylkill coal, Pottsville coal, so forth. Now, how is coal made? Mentioned before, it's kind of made like sedimentary rock. We have organic materials. So if you can think, like if you do your lawn work or yard work, you take all that material and you place it somewhere, and then you put some heat to it, you press it. Eventually, it'll turn into more and more dense and drier, and it'll turn into eventually coal, since coal is essentially just a form of carbon with other materials and minerals together. So you start with your organic carbon, and then you eventually get into anthracite. Kind of interesting that the way we have coal here in Pennsylvania is before North Africa smacked into us, there was a small inland sea. And so a lot of this, and it was full of wetlands, and a lot of this organic material from the dinosaur era was deposited in this kind of closed sea. And then when the North African plate hit up against us, it compressed it and created both the bituminous and the anthracite coals. Quick difference visually, if you ever, if you're hiking up in the northeast section of PA, you're gonna find anthracite coal much shinier. It's glass-like. It's heavier. If you go out west, bituminous coal is more layered. It's lighter. It feels like charcoal. Something, if you have a bonfire, you have leftover log, you feel the next day how light it is. It's closer to that density, but kind of interesting. I have a piece at work, and it's really, you look at it and it has so many different colors in it. It's very interesting. Luckily, one of the things that really helped the geology, the Susquehanna River Basin, and geologists in general, was the fact that because we had all this coal and it was mined out, we had a lot of really good maps of underground coal mines. And it really told us a lot about the structure of our geology in the Ridge and Valley province. Quick note here for this diagram, that center line that says datum mid-tide is in fact sea level, which I believe this is, where's the Coaldale incline? So that's about 1,200 feet above sea level, and you can see that the coal measures extend way below even the ocean line. So what's really important about this is the fact that if you look here on the eastern side, the coal measure there is almost straight up and down. And as it's twisted and pushed, it flattens out. So if you're mining this area, you got to design some sort of method. And if you're going straight up and down, you design another, which is why a lot of people think that the Pennsylvania coal miners from back in the day were probably the best at their job, figuring out geology and how things work. And they really helped propel Pennsylvania. Like I said before, because we have lots of different kinds of coal seams that are all every which way but loose, they had to design and designate very specific methods of mining this coal. Room and pillar is probably the most common people think of. There are some efforts where the fellows here were literally mining above their heads, and then down below there's the tipple, same thing, they're mining above their heads. And then here you see, as the coal tipple came out, they were sorted for slate and whatnot. And then here is another example. I think this is the Hazleton Slope. They just built the railroads at the angle of the coal mine. So it's very interesting working environment and unique geology there. So that about wraps it up for the Ridge and Valley province. And we're going to step to the Appalachian Plateau province. This is the most forested. It's the most idyllic. A lot of people have cabins up there for hunting. It's the PA Grand Canyons up there. It's a very unique and different place and beautiful as well. The Appalachian Plateau is actually a lot larger. Only a portion of it's in the basin, but we actually have the tallest part of it. That's why we have the PA Grand Canyon and whatnot, but it extends all the way down to Kentucky, through West Virginia and parts of Ohio. Essentially what happened is when Africa hit the North American plate here, right? The first step is it kind of metamorphosed all these rocks here. Then it kind of smushed these like fabric, right? Ridge and Valley. And then what it did with the Appalachian Plateau is it just lifted it straight up. In other words, it just kind of lifted it straight up. Here's the geologic map, and generally it's very uniform because there's not a lot of difference. It's mainly sandstone and shales. There are some dolomites and limestones up in the northeast part towards Cooperstown, but those are very small and thin. But generally speaking, these are sandstone and shale and very uniform geology out through there, which you can tell when you travel through the Appalachian Plateau from Clearfield over to Towanda. You generally looks about the same. It doesn't really have a lot of change, as opposed to, say, if you travel from Harrisburg at the Ridge and Valley start to Williamsport, you get a lot of variation. So here's another example of the Appalachian Plateau and what it actually means. If you go out, you say, oh, but hold on, it's not a plateau out there. There's a bunch of rivers and there's mountains. There are. But if you look carefully here, you'll notice the tops of all these mountains are generally about the same elevation. In fact, it wasn't the mountains that were uplifted, but it was actually the river. This is the Pia Grand Canyon here. There was the river that carved down. So you have a flat area here, and it's a river that carved down through it. So it's kind of interesting and unique, and I think it's gorgeous up there as well. To kind of show you what we're talking about here is this diagram's from a little bit south of us. It's below the basin, but it's a good diagram that I took from University of Eastern Virginia. And you can see here with the coastal plain, which we don't have, that's towards Philadelphia. But then we have the Piedmont, which we talked about. And you can see that crystalline rock, those diabases, and then the metamorphic rocks create those ridges. And then they call the Blue Ridge, I call South Mountain, what we call South Mountain. Right here is kind of the tip of it. Well, then this is the part of the African rocks, when it hit our sedimentary rocks here, or limestone or shale or sandstone, it warped the ridge and valley, right? So that's how you get the curves. But the pressure, when it finally stopped, the Appalachian Plateau here, it was just uplifted. In other words, there was no deformation. So it's a pretty unique, pretty simple system. So you can see how the pressures going from east to west change. And then one of the most beautiful things about the basin is that we have the Allegheny front. In other words, a transition from the Valley and Ridge province to the Appalachian Plateau. And I say this because I like to watch hawks and eagles. And this is a picture that I took at the Allegheny front. It's on its roadside. I forget what road I was on, by Snowshoe, I believe. But right here, you can see eagles and hawks because they can start at the Allegheny front, which is the top, and then you can see the Ridge and Valley province in the background. And it's just stunning. You can tell when you finally hit there, like, oh, we're in the Allegheny front. The elk and the wilds up there, Cinnamon, I think if you guys know about that area, it goes from being this very tall plateau with all this beautiful, and then all of a sudden you're down to the Ridge and Valley. That's the Allegheny front. It's really interesting. Now, the last part I want to talk about, since we are talking about the Susquehanna River Basin, is rivers and geology. How do they impact each other? The geology was there first because we don't know. We know the river is probably around 100 million years, but as I said before, for about 500 to 600 million years, we've had things happen to our basin. So it kind of impacts where the water goes. When it rains, the water wants to go downhill, and so the biggest control we have over it is what the rocks are. Even though water is the most powerful force in the earth, rocks come a very close second as well. And I want to talk about the types of drainage you get in streams to kind of close out here. Just to see that Pennsylvania is very unique, as we have the dendritic, rectangular, parallel, trellised, and deranged, which I don't know how they came with that name, but it is what we call it. The dendritic pattern here, this is the Allegheny Plateau, the Appalachian Plateau, sorry. And you can see here, it's dendritic because it looks like a leaf. It's a dendrite. It collects from areas, gathers the low point, and continues on. Pretty straightforward. This is probably what most people think when they think of streams in the typical stream section. Pardon me. And so it's very idyllic. This is where you get your canyons. You can see here there's a very deep canyon over here, and just your typical drainage pattern. The next two is rectangular and trellis. So those are kind of related. I don't want to get into the details of why they're technically different. It's very complicated and probably not worth the time. But we have both of those. And I took a screenshot here of one of my maps. This is north of Harrisburg. We're in the Ridge and Valley province. And you can see here how our streams have a trellis pattern. In other words, these green areas here are the top of the ridges, right? And so gravity wants to go down, and so it'll go straight this way. But it can't go any more south because there's another ridge here, so it has to go west. So it does this trellis pattern all the way down. And there's lots of examples through there. Rectangular, trellis, it's kind of neither here nor there. It's very interesting, and you can see here some of the streams that are actually channelized through the ridge and valley where they have nowhere to go. It has to go all the way down.
He's talking about this dolomite cliffs down.
The next one I want to talk about is the parallel drainage. And the great example I like to use is Cumberland County. This is actually where I'm from. Our family farm is on the Big Spring, which is somewhere down here in the limestone. But we have the Conner de Gwinnett to the north and the Yellow Breeches to the south. They don't join up. The parallel drainage typically occurs in limestone because of a lot of the underground groundwater. In fact, a lot of limestone areas, if you notice the difference between how many streams there are here versus where they are in the Cumberland Valley, it's because a lot of that is underground and through fractures and whatnot. So this is a parallel stream system, which we have that as well. Mostly in the Great Valley. There's a couple other areas as well down towards the diabases that are separated, but just kind of show you some of the examples. And all these kind of shape the way our basin is and how we use water, because as citizens of the Susquehanna River Basin, we rely on water, right? We need to drink, but we also rely on it for our crops. We rely on it for our animals, for industry, for numerous things. So water and rocks kind of interplay together. And the last one, deranged. I didn't think we had any in the basin. This is typically the deranged system would be like up in New York where you get a lot of wetlands and there's, a stream, or I'm sorry, a lake will have 6 or 7 different exit points, all from, not just one exit. But then I looked closer and I said, hey, you know what? Raystown looks pretty darn deranged. I'm not a big fan of that term myself, but so you can see here, deranged is where there is no concise pattern. It kind of meshes together. Water can go up and down and backwards. Not very applicable here because we kind of have a pretty set drainage here in the basin. So that's what I have here. I will conclude before I take questions to show you some of my favorite spots. There's a website called bucketlist.com. People post it. I posted there. And to show you the geology, how diverse it is and how beautiful it is in our basin. I just, spending an afternoon with the moss covered rocks. These are the sandstones here. This is up towards the Appalachian plateau. Here we have Devil's for the top of my head, it's a scree slope left over from glaciation. It's kind of surreal. It looks like a Martian landscape. And then this tree always cracks me up. It's like, yes, I will make it. I will make it. The tenacity of life, right? It's a little hard hiking, I'll be honest. It's probably more advanced hiking. Then we have some of these wind caves. This is up towards McKean County, up in the Appalachian Plateau. And the person who has an attraction there, he charges money, but he lights it up, and it's kind of a neat little thing. Chimney Rocks, I'm sure you guys heard of that. It's much more impressive in person. And then of course up towards Hazelton and Wilkes-Barre, we have Tipping Rock. That's left over from glaciation, and it really does seem like there's no reason why that rock should not fall down yet. But it's pretty interesting. And there's many more here in the basin. And I'll leave you here with a picture of the Pennsylvania Grand Canyon, also known as Pine Creek, in the Appalachian Plateau. Another great example of how the top of the ridges are generally the same. And there in the background, you can see part of the ridge and valley province, which is slightly taller. So with that, I will stop my share and take any questions. And there we are. I'll turn it back over to Kayla.
Thank you, Pierre. That was very interesting. I know I learned a lot. This was one that I was curious about just because of where we live and how people always say that like geologists come from I hear people say like geologists come from all over to study the Susquehanna, like especially in this area because it is so unique. So there were there's a couple questions coming in. James asked, what were the hikes that had the carved rocks again?
Oh, the fall. So it's Falmouth. You mean the diabase down towards, the potholes? I'm assuming that's what James is talking about. Yeah. So I forget the name of the trail, but if you search on the internet for the Falmouth potholes or petroglyphs, because there's also petroglyphs in Native Americans. I forget. You can get there from Falmouth. Falmouth is where I go, but I take my boat. So I can, when it's lower, my kayak. But the hike itself, it's closer to Chickies Rock. But yeah, that's where you want to look. And I do recommend that it's you can't see them every year. It's usually when we have very low water. So when there's a low water, there's usually a rush. Everybody's like, oh, hey, let's go check it out. So to go back to your question about the geology, it's interesting because when I went to grad school out west, um, the geology is so simple. I don't want to say simple. It's not as complex as Pennsylvania and the Basin, that just having grown up here and visited and lived here, I already had a leg up on a lot of geologists because I was exposed to so much geology, and it's really a resource that here we have in Pennsylvania and the Basin.
Oh, that's neat. All right, so Anne asked, is there scientific consensus on the formation of the water gaps?
Well, yeah, so there's a general broad consensus that when the Ridge and Valley was compressed, that the top part was not as ridgy and valley. In other words, it was much flatter, and so when the river started to form, it just found whatever the local variation was, and then once it was entrapped, then it was stuck and had to stay that way as it eroded. There are some other theories because there's also wind gaps where the river cut through and there's a notch in the valley, but there's no stream. There's general consensus that it's some sort of erosional feature that controls it, but there are some other ideas about glaciation having caused dams, which caused rivers to back up, which allowed the rivers to flow over the ridges that caused it. That's another potential idea. So,
okay. Let's see. Tina asked, what should we be doing to more effectively get the Chesapeake Bay cleaned up from the north?
From the north, from the river, you mean?
I think so, yeah.
On an individual level, it sounds, there's a lot of things we can do from a government level, but that's from an individual residential level is, if you have a yard, be cautious of your pesticide and herbicide use. Be cautious of if you have a small farmlet of sediment on your driveway. If you have a driveway that's still gravel, you keep in mind every little bit of drop of water that leaves your property goes to the Chesapeake Bay. So if you want to be mindful of what you put on your property that runs off when it's raining, then that's probably the best you can do. That and be active and talk with your legislators and your local environmentalists and try to help out.
Okay, and she did say that she meant nitrogen, not the north. Sorry, Tina.
Oh, nitrates are really, really hard because one of the largest problems is the fact that in areas that are more rural, in other words, that don't have public water and public sewer, a lot of folks depend on lot septic systems, and their nitrogen is just very hard to treat, especially in a small system like that. You could throw billions of dollars at it and run public water and sewer everywhere, but a lot of folks don't want their own their own bill and whatnot. So that's a hard one. Planting is probably what I recommend the most. More trees uptake nitrogen. If you can intercept that nitrogen, and it's fertilizer, right? Essentially. So if you can plant more plants and trees and uptake the nitrogen and keep it in the trees, then that's less going to the bay, and that'll help out. As far as farming and so forth, we're gonna have to help the farmers because it's hard enough farming, let alone trying to manage multi-billion-dollar issue of nitrogen and phosphorus.
All right. See, Tim asked, can you talk about the sinuous part of the Conde de Gwinnett near the river? I think I said that right.
Yes. So that's base flow. So it's a traditional. Well, a couple things. There's a ridge there. I think the ridge road, I think, is up through there. So the Conde de Gwinnett, as a stream, has more elevation and pitch. It goes faster, right? So if you're in a headwater stream, it's running faster because it's got a steeper slope. As the Conde de Gwinnett gets closer to Susquehanna, keep in mind the Susquehanna, right now I think it's around 5 feet. It's frozen, but during the Agnes flood, it was like 36 feet, right? Well, when it rises up 36 feet, it's actually going back up the Conde de Gwinnett. So when the river stops having the velocity to cut down straight, it likes to meander, and it's trying to find a way around from it. So the meanders, which typically occur when you have a small river down into the larger river, and it creates that meander. Just like the Mississippi, if you look at it in Kentucky and West Virginia, or Kentucky and Ohio, it's not very sinuous. Once you get down to Louisiana and Mississippi, then it starts making these huge S's because it's slowing down. So it's a velocity issue.
Okay. All right. Elise said, let's see, she asked, I've read in multiple sources that the Susquehanna is 325 to 340 million years old, older than the mountains, one of the 5 oldest rivers on Earth, already flowing on Pangea. Is this correct?
I don't have sources that say that. Pangea is about 800 million years old. So that's 340 million years ago is, I'm trying to think, we're probably in Laurentia. It's hard for rivers because rivers change. So what we would call the Susquehanna, was there a river of one form or another that existed? Yes, because it was raining. Was it the Susquehanna in the form it is now? Probably not. So it's kind of hard to figure out how old the Susquehanna is. The best determination we know in its current form is roughly 44, maybe 50 million years old, pretty much when the continent stopped pushing. But again, that's one of the things with geology is that, we weren't there. So, it could be very well true that the Susquehanna was there, and we're trying to do the best of the record we have. And some evidence points one way, some evidence points the other way. And it's hard to determine, 100% sometimes.
Okay. Let's see, Janet asked, how was Bluestone Flagstone formed?
Bluestone, so just to clarify, you mean the bluestone up north towards the upper part of the basin, or the slate bluestone that's down the Peach Bottom? I've heard both of them called bluestone.
Okay, let's see if Janet's still here.
Or I've even heard diabase called bluestone as well. I think towards Coatesville they call diabase bluestone as well.
Okay.
North. Okay, I saw it north. Yeah, so up north, the bluestone, that's actually worked at a project up there. It's sandstone that was laid down pretty normally, except that the quality of the sand that was put into it. So if you can imagine, you go to Hawaii, you get black sand, you get black sandstone. You go to Wildwood, you have white sand, you get white sandstone, or in this case, probably plastic sandstone, because that's what's on the beach now. But the bluestone up there is just a very unique fine-grained sandstone that actually has a little bit of shale in it, mud, and that cements it and gives it its color and its strength. And that's why it's very unique. I know it was used on the sidewalks in New York City for the longest time, and I've been to some of the old quarries, and it's really impressive. But for our best of our knowledge, it's just a very unique sandstone that was laid down with just the right minerals to create that color and that strength. But it was just laid down like any sandstone. There was no other fancy process. It's just like made like everything else.
That's neat. All right, Eric asked, why is the Susquehanna so unusually wide and shallow, especially around the Harrisburg area?
That's a really good question. And the reason why is the same reason with the water gap. So if you think logically, the river wants to flow from low to high. So in the ridge and valley, it wants to go east-west, right? So if you go up north to Dolphin, if you're going up, the rail trails up Stony Creek, it's going uphill, right? You would expect the river, but because we were smushed together and the river has to break through the rocks in the wrong way, instead of following the rocks along, right? It's going through the rocks. In other words, it spreads out because the rocks are so strong. It's so much harder to cut through a rock in a perpendicular direction than to go with the rock. And it's one of the unique things about the Susquehanna. It's always been known as, a foot deep and a mile wide. In fact, in Harrisburg, if it wasn't for the Dock Street Dam that raises the river level about 3 feet, during the summertime, you could almost walk across the river to the West Shore from Harrisburg. And there's more information historically. Meyerlode Dock was instrumental on actually cleaning up and helping the river there. So, but yeah, it's wide, specific, which is interesting because it's wide in Harrisburg, but you go about 20 miles south to Marietta and it's 35 feet deep. It just changes so quick. Yeah.
Cool. All right. James asked, does the Susquehanna River Basin Commission do any volunteer work, like picking up trash or like things like that?
Yeah, we do days of volunteerism. We do, I think there's some of our staff work with the green belts. There's people who do, I work with the green belt trash pickup. There's, it's more individual basis, commission wide. We don't have a lot. We have some Earth Day celebrations. We do a lot more advocacy as far as education. That's more of our volunteer work, things like this, for example. But that's something that going forward, I could definitely see that we could do more of. In fact, I know we just hired a new person, Stacey Hanrahan, who's much more excited, so she might be more involved in that. So hopefully we can do a little more volunteering.
Okay, is that something that anyone might be able to help with, or is that just for like employees maybe, or is that still being worked out?
I think it's still up in the air. I don't think we have a program in place right now. I think Stacey's actually on this, so I'm sure I'll get an email here shortly about, oh, well, I've got some ideas. So yeah, that's a very good question though, and thank you for asking it.
Sure. And then I have a question. You mentioned about, you brought up a picture of the Devil's Race Course that's there in the Stony Creek. So How that, I love going there, and I think that's one of the coolest things, but how, do you know how that was formed?
Yeah, so that's a periglacial element. So I'll back up real quick. So there are two things to glaciation. I didn't really touch on glaciation because I didn't know how much time we had. And like I said, one of the problems with geology is that I could talk about this for a week straight. So it was hard to pare it down. So glaciation, in your mind, you have the glaciers come through and carve out a valley, right? But more importantly, when you have a glacier that's close to you, so for example, Devil's Raceclass is a great example. Glaciation did not make it there, but because there's a glacier there, it's really cold at night, but during the day it heats up. And what it does is it cracks the rocks, and then the rocks flow down with the mud, and then the mud disappears. So it was formed essentially by cracking the rock, and then there was so much rocks that nothing, it's deep, it's like 50 feet deep full of that rock, and nothing can grow in it. So what's interesting about the Devil's Racetrack is that if you actually go, 2 miles, I think it's east, you have the same thing, except that it's only about 5 feet deep, and so there's trees in it. So the only reason that formation is so unique is it's deep enough that nothing can grow in it. That's why that one tree is so spectacular. So if it was shallower, because we have all over Pennsylvania those kind of formations, if it was shallower, then you wouldn't get to see it.
Okay. Oh, that's neat. That's what I was there with my family, I think last year, and they were like, you should know this stuff. Like, why is it like this? I'm like, I don't know. And then you mentioned that tonight, and I was like, oh, I have to ask him that. All right, so then let's see. Janet also asked, is the fracking up north affecting the water quality in the Chesapeake?
Oh, that's a question. So I would point you to, we did a study of water quality regarding to natural gas in the basin. It's on our website to check it out. And it's the fracking for the Chesapeake Bay. I think the biggest issue is probably farming and uncontrolled sewage from online septic systems are probably the two largest issues we're dealing with for contamination. As for fracking, the largest issue with fracking is actually not the fracking, it's actually the roads to get to the fracking. So like I said before, the Appalachian plateau up there, pretty pristine, very forested. For every pad you have natural gas, you have to build roads and pads. And so all that sediment comes down to the rivers. That is probably the most detrimental to the Chesapeake Bay. The fracking itself is not, it's just the access, but you can say that of if you built, 100 houses up there or build a shopping center. So it's much more about the disruption of existing systems than the fracking itself. I mean, fracking is not without its problem. Obviously, I can't speak much to it. I'm not a petroleum geologist, but that there might be some better resources out there for us. And I would definitely point you to what my colleagues did about the pollution and fracking and how it relates to the basin. Might find some more information there. I think Stacy just put it up in the chat too, I think.
Yeah, she let's see, Stacy put up the SRBC website, and Hillary said to check out the reports library on the srbc.net.
Thanks, Hillary. I could not do my job without Hillary. I'm just telling you right now. Like I know she volunteers a lot for Wildwood, and
she's great.
Yeah, she's awesome.
All right, and is there one more? Oh, Eileen asked if the picture behind you happened to be from Heiner View.
So to be honest, we were using this new platform here, and I'm not in my office because of some issues with our internet at work. And so I literally just grabbed the first picture I could find. So I am not sure. I'd have to look it up.
It almost does look like it might be, but yeah, I'm not sure either.
Yeah, I usually have a suite of different photos behind me, but I forgot that they're on my network and I can't connect them. Oh. So no, I don't know. I'm sorry.
It's okay. All right. Tina also asked, does SRBC do like creek and river water sampling like the USGS does?
Yes, absolutely. Actually, that's one of the largest missions we have. It's in our monitoring and protection program. In fact, I believe one of my colleagues, Aaron, will be presenting here in a few weeks about eels, if I'm correctly. And so he's in monitoring protection. They do a wonderful job of sampling both for the EPA, they help with the USGS, and also for ourselves. And we actually have a live monitoring system that you can go on our website and actually check it. And we have reports. That's one of our biggest missions. We do assessments of fish, habitat, water quality, eels, and Aaron will get into that. But yeah, that's a much larger portion of what we do. And I would actually defer to Aaron maybe in a couple of weeks. That might be a question for him.
All right, I'll save that one. And Tina, maybe if you're not registered yet, you could sign up for that one too. And to say that's all the questions that I caught. I think that's all of them. And I don't think I have any more questions. Did you want to add anything to?
No, I mean, again, thank you for the Friends of Wildwood. When I have, especially during the wintertime when, I'm stuck in the house, going and taking a hike or a bike ride around Wildwood is very, very nice. And I really appreciate what you guys do to have this little gem in the city. And we have a riverfront park, but it's not the same as Wildwood. Wildwood's, just staring down at the water and the fish and seeing the birds and so forth. So I want to thank you guys a lot for what you do. I know it's a hard job, and it's a lot of volunteers and so forth. And then second, I'd say the best part about the Susquehanna River Basin and our geology and so forth is get out there. There are some amazing things that we have in the basin that people explore. A lot of people kind of poo-poo Pennsylvania and so forth, but I've traveled around the world, and it's one of the most beautiful places in the world, and you just can't get around that. When I left to go to school and left Pennsylvania for 4 years, I missed it. It just wasn't the same. So that's all I would say is, go out there, enjoy it. We have some of the best in the world. So
I agree. Yes. And thank you very much, Pierre, for agreeing to do this presentation for us. And we really appreciate it. And all the work that you do at SRBC as well. And everyone at SRBC does. And like Aaron said, he threw, or Aaron, wow, you're Pierre. Aaron's going to be here in 2 weeks. So like you threw
yes.
the pitch for Aaron, if you're watching this and you haven't signed up yet, Aaron is going to be here in 2 weeks for our next lecture to talk about different species of the Susquehanna River, including the eels and things like that. So in water quality, I think a little bit. So yeah, if you haven't signed up for that, feel free to sign up and join us for that. And I think I'll end it here. So thank you again, Pierre, for doing this with us. It was absolutely wonderful. I learned a lot. I know a lot of people did. Everyone thought it was spectacular. So thank you everyone for joining us. And we hope to see you in two more weeks for our third presentation.
That sounds great. Thank you very much. Appreciate it. Everyone, thank you for listening in. Have a good day. Have a good night.
Thanks, you too.